This video will be on catenary curves. Shout out Professor Michael Farquhar for teaching me how to do this. He says that British people call them catenary curves, so if there's any British people watching, hi. So chains and cables, right? Like if you have like a chain, I don't know, let me see, I can't really draw. Pretend this is a chain, and it's held up on both sides. This chain here, it's under its own weight. Or like if you have like cables, right? Like if you look outside and you'll see like landlines and just cables for electricity and internet. In essence, chains and cables create this certain type of curve where if it's under its own weight and it's supported only at its ends, then they are examples of what's called a catenary curve. And catenary curves can be described by using hyperbolic functions. Now let's look at some example properties of hyperbolic functions. By the way, have you guys ever noticed that like if you go to a mathematician and you're like, "So, who's your favorite mathematician?" They'll be like, "Well, I can't pick a favorite mathematician, Euler." Right, and now for you, I have written out some example properties of hyperbolic functions as well as the derivatives of hyperbolic functions, and I showed what the hyperbolic functions are made up of for sinusoidal h of x, for cosinusoidal h of x, and for tangent h of x. Go ahead and kick off a example question here. It says to find the x-intercepts of the following function. F of x equals 17 over 15 minus cosine h of x. Now for a problem like this, it seems relatively straightforward, right? The x-intercepts just means that we want to figure out where 17 over 15 minus cosine h of x equals 0. Where does 17 over 15 minus cosine h of x equals 0? Well, the x-intercept is equal to f of x equaling 0, in other words. Okay, so the x-intercept equals f of x, which equals 0. Now let's go ahead and rewrite this. Previously, we've already established the definition for the hyperbolic functions, including the definition for cosine h of x. It's defined as Euler's number raised to the power of x plus Euler's number raised to the power of negative x over 2. What that means is that we can rewrite f of x. And now we have something that looks a little bit different, but it still means the same thing. It's just of a different form, if you will. Now, to clear the fractions, we need to multiply by 30 because that's going to be the lowest common denominator of 15 and 2. The multiplication of 30 will clear the fractions. Let's see, 17 plus 17 is going to be 34, plus 17 is going to be 51. Throw a 0 on it, and it's going to be 510. 510 divided by 15, that's going to be 34. There is a negative sign here, okay? So we are subtracting. We're subtracting the binomial of what we get when we divide both of these two numbers by 2. In the numerator, we see 13 times e raised to the power of x plus 13 times e raised to the negative power of x. And in the denominator, we see 2. So we have to divide 30 by 2, and that's going to be 15 times e to raise to the power of x. But then we have to divide this 30 by 2. So what we'll get is 15 times e raised to the power of negative x. And this is a binomial. Now, this is where it gets a little bit tricky. Because this is a binomial, we're going to distribute this negative sign to the first term and the second term. The other day, my professor called this the rainbow. He said, "Oh, it's the rainbow property," and I thought that was pretty funny because it kind of looks like a rainbow, especially if you have like a trinomial. You can like add another one. Anyway, I digress. So this will be equal to 34 minus 15 times e raised to the power of x minus 15 times e raised to the power of negative x. We want to eliminate this term right here, e raised to the power of negative x. We want to eliminate it. So in order to eliminate it, we're going to multiply the entire equation by negative e raised to the power of x. So I'll throw some parentheses on here to indicate that this is going to be multiplied by negative e raised to the power of x. This e will get distributed to negative 15 times e raised to the power of x, and this will cancel. Ah, but then this 15 will become positive. Then it will get distributed to the middle term, negative 15 times e raised to the power of x, which is going to not only make this positive, but there's also going to be a 2 in front of the x in the exponential place. Then this 34 right here is going to become negative, and then there is going to be an e raised to the power of x attached to it. So by multiplying negative e raised to the power of x, we simplify the equation into a standard quadratic form with a positive leading coefficient. And this is what we'll get. So now this is in what is called quadratic form. What I'll do now is make more room. Now that we have this equation in standard quadratic form, we'll substitute. Beautiful. The equation will now be written as follows. Eureka! We can now apply the quadratic formula. I'll write out the quadratic formula because I think it looks cool, but also to be thorough. Okay, so we have the quadratic formula written out and we need to identify the components. So A will be the first term, which means that A is going to be 15. B is going to be the second term, which means that it's going to be negative 34. Remember that negative sign comes with it. That looks terrible. There we go. And now we'll find C, and C is going to be 15, the last term. Let's plug everything in. I'm going to simplify. Who wants to see lattice? I know y'all are trying to see some lattice. This is called Chinese multiplication. Now, when I was younger, I never really understood the American way to multiply it. They're trying to say like that these numbers like went to a dance together and there's like a bow tie method and they're like, oh, it has to get dressed. And I'm like, no. But then in third grade, my professor, or I guess rather my teacher, Miss Latimer, showed me this way. So you set it up like this. So and then you do 4 times 3, which is going to be 12. And then you do 3 times 3, which is going to be 9. And then, oop, this is supposed to be a 0. You have to fill it in with zeros if there's nothing there. And then 4 times 4 is going to be 16. And then 4 times 3 is going to be 12. And then you just add them up. 6, 2, 5. And then you do 1 plus 9, which is going to be 10. And then plus 1, which is going to be 11. And then you put a 1 there, and then you carry the 1 over. And then you can put it in this place. And then it's going to be 1,156. So yeah, the numbers didn't go to the dance together. That's going to be the answer to negative 34 raised to the power of 2. And it's going to be a positive because every time that you're raising a negative number to an even power, it's always going to be positive. That's just the way that it works out. You guys, it's so hard not to make jokes while I'm doing this. Like, I make some little jokes here and there, but like, I really want the math community to take me seriously. So, like, I'm holding back. This is me holding back, by the way. So, 15 times 15. Let's do lattice. It's going to be 225. 225 times 4. Well, we can do that in our head. It's going to be 450 plus 450, which is going to be 900. Let's try to do this one in our head too. 1,156 minus 900. Is it 256? I do believe it's 256, but we're getting ahead of ourselves. We have to do 2 times 15, which is going to be 30. And now we can do 34 plus or minus, what did we say it was? 256. Is it 256? I might have to G-check that, dude, because I'm not 100% sure. But I do know that 256 is a perfect square, so I would imagine that it is 256. So we're not going to check that. Um, no, I should probably check that. Yeah, it's 256. So then the square root of 256 is going to be 16. So we'll have 34 plus or minus 16 over 30. And then there's going to be two answers. The first answer, it's going to be if we do addition. So 34 plus 16 is going to be 50. And then it's going to be 50 over 30. I'm pretty sure, right? And then we can simplify that. They're both divisible by 10, so it will be 5/3. And then uh, this is a little bit more difficult here, but we'll do 34 minus 16, which is going to be 18. I'm like pretty sure it's going to be 18. And this is if we go the subtraction route, so it'll be 18 over 30, and these are both divisible by something. So 30 is divisible by 6 because 6 times 5 is 30. So that means we'll put a 5 down here. And then 18 is divisible by 6, and that it becomes 3. And so like I'm pretty sure these are our answers. That means that 5/3 equals u or 3/5 equals u. Let me grab some room. Okay, so we have 5 over 3 equals u or 3 over 5 equals u. So from here, what we can do is we could back substitute. If u equals e to the power of x, that means that by definition, e raised to the power of x equals 3 over 5, or e raised to the power of x equals 5 over 3. Now there's something interesting that's going on here because we see that 3 over 5 and 5 over 3 are reciprocals of one another. I can say that x equals the natural log of 3 over 5 or x equals the natural log of 5 over 3. Then what we're going to do is we're going to use a technique that involves the application of the natural logarithm formula. This is the natural logarithm formula, and we'll apply it. Because of this formula here, it means that we can pull that -1 out front, and so we'll do so. Now this is the same thing as just negative natural logarithm 5 over 3. Therefore, we'll find that x equals plus or minus the natural logarithm of 5 over 3. That's our answer. All right, so we're prompted to find f prime of x for f of x equals x squared cosh of x. Now there is a product rule. F prime of x equals x squared prime times cosh of x plus x squared times cosh of x prime. That means that we need to find the derivative of x squared. Written in blue is the rule for taking the derivatives of something that's being raised to a certain power. So we can apply this here. F prime of x equals the derivative of x squared. What's the derivative of x squared? We're going to pull that 2 out front. X subtract 1, it's just going to be 2x if I'm not mistaken. And then it's times cosh of x, so we'll just put cosh of x. That's what it means. You're multiplying them if they're next to each other. That's what that means. And we're going to leave this x squared here alone, so we'll say just plus x squared. And then we need to find the derivative of cosh of x. And if you remember from before, the derivative of cosh of x is always going to be sinusoidal h of x, or sinh. We call it sinh in my class. So we'll do times sinh of x. That means that this is going to be our answer to finding the derivative of f of x equaling x squared cosh of x. So hold on, let me get that looking. Ooh, 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 ooh. Let me get that looking nice. All right. So at this point in time, we're told to integrate the indefinite integral tangent h of x. And to do this, we need to rewrite tangent h of x. Now, we've already established that tangent h of x equals sine h of x over cosine h of x. Now, because sine h of x and cosine h of x is the same thing as tangent h of x, we can rewrite this integral right here. Anytime we have a fraction where the numerator is the derivative of the denominator or a constant multiple of the derivative of the denominator, we'll likely use u substitution. We know that sine h of x is the derivative of cosine h of x. Therefore, we're going to substitute and we're going to set u equal to cosine h of x. Okay, now we'll take the derivative of cosine h of x. I just got deja vu. Therefore, du can be set to sine h of x. There should be a dx right here. Sine h of x can actually be moved to the side, and we can stick a 1 right here. Now, cosine h of x was set as u. Therefore, we're going to go ahead and stick a u in the denominator, and du is sine h of x, so we'll put it off to the side here, multiplied by du. What to do, what to do. The integral of 1 over a variable. This is a special case of the power rule, and we're going to apply the logarithmic rule for integration. Let me show you what that looks like. The integral for 1 over a variable, in this case x, with integration with respect to x is going to equal the natural log of the absolute value of x plus c, of course, because this is a indefinite integral. We'll go ahead and apply this. So we got the natural log of the absolute value of u plus c. And then, of course, we're going to back substitute. So it's going to be the natural logarithm of what we set for u, which is cosine h of x plus c. And that's going to be our answer. So we're asked to integrate the integral from 0 to the natural logarithm of 2 for sine h of 3x, and we're going to integrate with respect to x. All right, so this case is a little bit different. What we're going to do is write down the general formula for integrating sine h of a coefficient that's in front of the variable. I'm going to have some fun with this. Wait. Right, so this is the formula that we're going to apply. Now, please note, I use the Greek letter psi. I just think it's cool. It's a placeholder variable, or you could call it like a interchangeable variable. For an example, these are the same exact formula. I just changed psi to the English letter K. I like psi. I think it's cool because Poseidon. Now, enough talking about the formula. Let's actually apply the formula. Note how there's a 3 right here. Thus, when we integrate it, that 3 is going to come down, and we're going to have 1/3 cosine h of 3x. And then we're going to be integrating from 0 to the natural log of 2. Now we shall apply the fundamental theorem of calculus part 2. Now plugging our bounds of integration into the function, this is what we'll get. How are we to evaluate cosh of 0? Well, let me tell you something. If you go on your TI-84 calculator and you go into the catalog, you'll find the cosh function, and you could plug it in like that. But it might be a good idea to commit the fact that cosh of 0 equals 1 to memory. Now, the thing about cosh is that it's actually a form of Euler's number e, the exponential. So feeding it a natural log, something should cancel out. Go ahead and grab some room. Now we've established that cosh of 0 is going to go to 1. So this will become 1/3 cosh of the natural log of 2 raised to the third power minus 1/3. All right, so cosh of x equals e raised to the power of x plus e raised to the negative x power over 2. Now, this does look rather intimidating, but let's just work through it. 2 raised to the power of 3 is 8, so we'll put 8 in those places. This here, e raised to the power of the natural log of 8 is going to become natural log raised to the power of 8. Then we'll have plus e raised to the power of negative 8. And then down below in the denominator, we'll have a 2, and we'll subtract that 1/3. We'll multiply this 2, and we'll multiply this 3 here. And this is actually going to give us 1/6 times 8 plus e raised to the negative natural log of 8th power minus 1/3. Something to note here. My apologies as this overlaps, but note that e raised to the power of the negative natural log of 8 is equal to e raised to the power of natural logarithm of 8 raised to the power of negative 1. And that's equal to 8 raised to the power of negative 1, which is, of course, equal to 1/8. We have 1/6 times 65 over 8 minus 1/3. This is our answer. This question says, show that the arc length of the catenary curve y equals cos h of x over the interval 0 phi is equal to sine h of phi. Couple things to note here. The first thing is that phi, this variable here, this is just a placeholder variable. I think it looks cool, so I decided to use it, but you could put anything you want there. You could put A, you could put B, you could put C, you could put whatever you want. I just chose a letter from the Greek alphabet, but it's interchangeable with other variables. Now, in order to find the arc length, I need to know what the derivative of y equals cosine h of x is. So we have cosine h of x, and I want to know the derivative. The derivative of cosine h of x is going to be sine h of x. What's more is we need the arc length formula. I'm going to plug in what we have identified as the derivative of cosine h of x, and I'm going to plug that into the arc length formula. Right, so this is what it looks like when we plug in our components to the arc length formula. The square roots don't cancel because the square roots do not split amongst the sum. They're not separate and they are together. So what we'll do is we'll use an identity. Now we have this identity here. Cosine h squared of x minus sine h squared of x. And that's going to equal 1, which means that we can rearrange this and manipulate it. All it says is that cosine h squared of x equals 1 plus sine h squared of x. So what does this mean for our integral? Well, it means that if we plug this identity here into our original integral, we can actually change it to the definite integral from 0 to phi of the square root of cosine h squared of x. Now, how are we going to solve this? Well, only now will the squares cancel. And then the antiderivative of cosine h of x is going to be sine h of x. The derivative of sine h of x is going to be cosine h of x. So let's go ahead and take the antiderivative. And now sine h of 0 is just going to be 0. And let me show you why. This is why sine h of 0 is going to be 0. Because you remember how these were x's before? Well, now we're going to plug in 0 for them, which of course is going to turn into 0 over 2, which is just going to be 0. Thus, we'll look at this right here, sine h of phi. And I'll say that the answer to this problem is going to be sine h of phi. And that's how you do that. Thank you for watching.